Hi, everybody. Hi again. I suppose quite a few of you will have seen the Reactive Spring live demo session with Josh. Just maybe a raise of hands. Who has seen Reactive Spring this morning? As far as I can tell, that's quite a few hands. Inverse check, who has not seen Reactive Spring this morning? Okay, that's equally all right. This session is quite independent, and it's a very different perspective. So with my background as serving as the Spring Framework project lead since the dawn of time, since like 2003, serving as the release manager and the lead of the core framework project, this is still the case today. And I'm very involved with not only the general strategy at the core framework level, but also with a lot of the core container features. So I'm taking the opportunity here with you today to talk about some of the recent work we've been doing, some of the recent work I've personally been doing at the core container level. And I'm going to spin it along three sort of themes. We're going to talk about a kind of initiative, the core API revision, that we're going through for a number of years already. We're going into the performance topic, so we're going to talk about different aspects, different characteristics of what it means to tune the runtime behavior of a Spring-based application, and with lots of forward-looking topics in there. And we're going to revisit reactive, the reactive topic towards the end. It's not the focus of this presentation, but we're going to go into the reactive topic again a bit from a programming model perspective, from the perspective of designing endpoint arrangements with reactive API types and how we go about this, because some of the specifics of how we actually integrate reactive programming into our general programming model story are not as well known as they should, I guess, right? All right, and all of this at Spring Framework 5.2 level. Quite a few things I will be talking about have been introduced in like 5.0, 5.1. We generally see the Spring Framework 5 generation as the frame that we're working within, and then like roughly once a year, we do a minor release, but a very rich minor release. So both 5.1 and 5.2 introduce a lot of new stuff, in the details at least. I mean, with 5.2, there's also a lot of high-level stuff like RSocket support, reactive transactions, but in particular in the details, refining the API surface, fine-tuning internals, fine-tuning extension points. There's a lot of work, and we're not at the end of this line. We're working towards a 5.3 release, probably September next year, when that one will be final. And it looks like there will also be a 5.4 afterwards, so we'll keep along this line of evolution. All right, so much for a bit of an introduction to the core framework topic. So that means stuff we're not talking about today is, in this particular session, is higher level stuff. We're not going to talk about boot much and only going to refer to Spring Data a bit. We're really going to stay at the Spring Framework level, quite literally meaning GitHub, Spring projects, the Spring-Framework project on GitHub. That's kind of the frame for our discussion today. All right, so what do I mean by core API revision? There's plenty of stuff happening at the surface area. Spring is known to have a quite large API surface. It's a very, well, I guess an approachable framework approachable from many directions. There's a lot of programmatic interaction that you can have with Spring Core Container facilities. And this is, of course, dating back to like 2002 in its origins, 2003 in particular, where lots of those initial API design decisions have been made. So in the past like 2 or 3 years, we are on a mission, which is still ongoing, still continuing, where we took the opportunity to raise the baseline to Spring Framework in Spring Framework 5 to the Java 8 level. Java 8, of course, presents a lot of goodness, not only for applications, but also for framework providers, for framework API authors. The The baseline in Spring Framework 5 is new for us. It brings a lot of possibilities in terms of API design on our end, API extensions, adding overloaded methods for Java 8 purposes. I have to add, it might be more relevant for close integration with the framework than for applications, because in applications, of course, there was already strong Java 8 support in Spring Framework 4. Like in Spring Framework 4.3 in particular, there was already very comprehensive Java 8 support. But the framework itself in Spring Framework 4 was Java 6 based and only had optional Java 8 support that was automatically kicking in whenever you were using it on a Java 8 runtime. So in many ways, Spring Framework 4 felt like a Java 8 based, Java 8 oriented framework already. Like for your purposes, for application development purposes, that was our goal. Now in Spring Framework 5, finally the entire framework itself, its entire programmatic service area, and all of its internals, the entire code base, have been revisited for a Java 8 Plus upgrade. So while you were able to use lambdas, method references, Java.time duration, instant, local datetime, all of this stuff, this Java 8 stuff, you were able to use it in your code and we automatically adapted to it. Now we're also able to introduce it to our code base. And there's a few things we can only do now, or we were only able to do in the Spring Framework 5 generation. And it basically comes in with two particular lines of work. The one is about Java 8 API types. Previously, we could only optionally support them when we called a handler method of yours or the like. Now we can have hard references to them in core container API types. So you'll find methods in Bean Factory, in Object Provider, at JDBC template level, and all of those levels are now open to having hard Java 8 API references in them. So we can have overloaded methods that return completable futures, that accept a configuration value as a duration or an instant. We can have methods that return a Java util stream, right, a collection stream. We can also have some more efficient interaction with Java 8 APIs in some of our SPI contracts. Most importantly, we now have the set of Java util function interfaces available to us as common ground for lambdas and method references to be bound to, like Java util function, supplier, consumer, of course. We make good use of those methods. They are also a common ground in interaction with other libraries and other frameworks, and they are commonly used in Java util collection streams. So Java 8 itself comes with a very in the meantime, well-known collection stream arrangement. We're trying to align with it from an API design perspective. So that's one part, and the other part is default methods. Java 8 has this nice little feature in interface design where methods in an interface can be declared as a default method with a body. So the method basically comes with an implementation at the interface level. Now, this is primarily a tool for evolving existing interfaces where additional methods added are declared as a default method so that existing implementers are not bound to implement a new method. They keep working. This is in particularly useful for convenience overloads or just simple methods with additional parameters that can easily delegate to another interface method. It's mostly a backwards compatibility feature for existing interfaces, and we're making some use of this. In the Spring Framework 5.1, 5.2 lines in particular. However, we also chose to redeclare existing methods for convenience purposes. So you'll find, if you look closely, you'll find quite a few existing methods, in particular in SPI contracts, in handler interceptor, in bean post processor, in some of those good old SPI contracts in Spring. You'll find that those are declared with default methods now. So instead of having to implement all of the methods in it, you choose to implement only the ones that you care about, and the rest come with a default method implementation with a just stubbed out no-op default behavior implementation. So there's no need for adapter classes or base classes to derive from. You can just do a straightforward implementation of the interface with very minimal code, only the part that you care about. There's another theme Java 8 baseline is one, and it provides a lot of goodness and richness to work with in our API evolution efforts. There's the other theme, and that's nullability. We encountered nullability from several angles, where it turns out that the API service that we had, of course, had many cases where it was a little unclear from just a look at the method signature whether this could return null, or in which situations it could ever return null or not. The same goes for incoming parameters. Can this be null? Or but it's more important for return values, where framework methods return something to you, and you need to know whether to be defensive against null values or not. There was kind of a general sense of this being a bit of an issue with nullability declared in the Java doc comments, even when working with Java. But then along came an even stronger force in the form of the Kotlin compiler. So in Spring Framework 5, we started to fully embrace Kotlin as a first-class implementation language for Spring-based applications. And it turns out that the Kotlin compiler has a few interesting twists when interacting with Java APIs. One of them being that a call to a Java API, like when your Kotlin code at the application level calls, say, bean factory get bean or some JDBC template method, the Kotlin compiler would always defensively assume that the return value can be null. So you can't assign it to a non-null variable declaration within the Kotlin type system. But that is quite common and quite idiomatic in Kotlin to do this, to have non-null assignments. So how can we get there, that our core container and the JDBC template and so forth, API surface, that all of this can be a good citizen in a Kotlin scenario? We figured that the Kotlin compiler has rules where it uses nullability indications through annotations usually, and it even has like a here on top of the standard JDK APIs declaring those. But for third-party libraries, the recommended strategy was nullability indications through annotations. And that wasn't news to us. We knew that this existed. There was JSR 305 as an effort that never really was fully embraced by the JDK. There were other libraries doing this already. So we figured we'll do this as well. Joining the club of RxJava and OK HTTP and others in fully declaring nullability through the use of nullable and non-null annotations across our entire API surface. So with a formal annotation, essentially for every parameter and every return value, giving a clear, formal, reflectively available indication whether this particular value can be null or not. Since in our API design efforts, aligning with Java 8 collection streams and other more like functionally minded design guidelines, we figured that non-null is actually the ideal default. That for many APIs that we want to take forward or that we are introducing, we'd like to define them in a way, to declare them in a way where most of the arguments and return values are ideally non-null by default. So that's what we went with. Non-null by default, it's declared at the package level through basically non-null API and non-null fields declaration for our packages. Tools understand this as a non-null default, and only exceptions to this rule are annotated with @nullable. So whenever you look at some Spring API, even at the Java doc level or diving into the source code that comes along with the Maven dependency, you'll see basically a hard declaration. If there's no nullable annotation, it will never be null, and it cannot be null when going in. If there's an @nullable on it, you need to be defensive against it. There's great tool support for this. We, in particular, learned to appreciate the tool support in IntelliJ IDEA. The constant conditions and exceptions inspection in IntelliJ IDEA is great in validating the assumptions that you make against those nullable fields or nullable return values. It will highlight, basically with a little red line, every single mismatch, where, in both ways, right, where a null value might come out of it, but you're not checking against it. You might run into a null pointer exception, but also the other way around, where a value will never be null according to the API declarations, according to the call chain, but you're adding a non-null check, an unnecessary non-null check. So it also indicates overly defensive code. that can be streamlined. We did this to our own code base. We went through the entire framework code base and made it strictly adhering to nullability rules from top to bottom and back up again. So also, not only for the surface, also for all of the internals, which was a really interesting exercise to go through. We found many spots where we were overly defensive in particular, and we refined quite a few APIs where we are a little bit stricter now in never allowing null as a return value in particular. So this is an ongoing effort. There's a collaboration with some industry stakeholders, Google and JetBrains among them, in a kind of well-defined set of annotations to use. For the time being, we're using our own. So it's Org Spring Framework Lang annotations for nullability. They are understood by default by IntelliJ IDEA and by the Kotlin compiler, and it's easy to set up those rules for other IDEs. I recommend doing that in your application setups as well. If you're interacting with not only Spring, but also RxJava, OK, HTTP, anything else, setting up those inspections and those validations in your own application project will make, like IntelliJ IDEA, validate the assumptions that you're making in your code against the framework APIs that you're calling. So there's this nicely transcends the barriers, the borders between application code and framework code. So it's also a value that we provide to the application level very directly. Now, to give you an indication, before we move on beyond nullability, to give you an indication, let's connect it right here with those few new methods we have on Object Provider. Object Provider is a little piece of indirection that we support at the core container level. Object Provider of foo is basically an indirect reference to your type foo, right, to the dependency that you're declaring. Instead of injecting a foo instance directly, you'll get an indirect handle to foo, lazily resolvable, resolvable on demand, resolvable in particular if there's a lifecycle mismatch, like a request scoped bean or a prototype bean used in from a singleton service instance. So Object Provider has quite a few use cases where it's useful. It can be obtained through annotation-based injection. At AutoWired, just declare Object Provider of foo. And as of 5.1, there's also a programmatic variant. The get bean provider on the bean factory returns the same kind of object provider handle for programmatic purposes. Now, aside from Object Provider's general role, there's a few nice little API twists here. Traditionally, at Spring Framework 4, Object Provider had getIfAvailable and getIfUnique methods. It also had a getObject method, but for our purposes here, getIfAvailable saying, if a corresponding instance is available, give it to me, otherwise return null. If there's a unique instance, so a single candidate to go with, not more than one, then getIfUnique will give that instance to you, or null in any other scenario. Now, that's how they were defined. That's what the Java doc said. Now, in Spring Framework 5, we redeclared them with an @nullable return value, giving a clear indication through the annotation here. It's literally part of the signature, where, for practical purposes, where that nullability indication is also expressed with a formal annotation. We didn't stop there, however. We went along and revisited our API design perspective, in particular in these places. Like getIfAvailable, getIfUnique is kind of common in Java to do it like that, but it's not very functional, right? So we introduced a couple of overloaded methods. GetIfAvailable, taking a Java util function supplier, allows us to redefine the rules, right? If that instance, if a managed bean instance is available in the container, return it. Otherwise, return the instance produced by the given supplier. And the given supplier is usually a method reference or a lambda expression that you pass in there, bound to a Java util function supplier. With those rules in place, their return value will never be null. You'll get the container managed instance or what your supplier produced, never null. So the return type signature here does not say @nullable. And this makes an important impact for your caller assumptions that you're making, and in particular for the aforementioned Kotlin assignment semantics. But we didn't even stop there. We introduced a further variant called, like in this case, IfAvailable and IfUnique, where it's even more functional, where you're saying like, if a managed instance of this type, of the declare type is available, here's a consumer, give it to me, I'll do something with it, I'll process it, I'll add it to some data structure of mine. If it's not available, skip that step. So this overload, if available with the consumer, is actually quite useful in practice for these sophisticated container interaction purposes. Now, in recent efforts, Object Provider also got enhanced with with allowing access to multiple matching instances. Previously, it was always only talking to a single matching instance. We recommend now to do like Object Provider of foo if you have to make an assumption that there might be more than one instance of this target type. You could do list of foo or set of foo. We still support it. We used to support it before. It's still there. But this is actually more expressive and semantically clearer. If you say like an indirect handle to foo, and yes, I'm willing to iterate over several matching instances, there's a classic iterator method on Object Provider now for potentially more than one matching bean instance in the container. And there's also a Java util stream method. Actually, there's two of them. There's a stream one and an ordered stream one. Stream has fully lazy initialization semantics. Only the instances that you actually process over are going to be initialized. And ordered stream is a little more aggressive in its initialization semantics in order to determine the order of those beans. So slightly different lazy versus eager init semantics there. But this is now our recommended way of interacting with several matching instances of a particular dependency type in the container. And it's also a nice example of our Java 8 design mission, right, that we're on here. Iterator may be a little classic, but stream is literally modeled along the lines of a Java util collection stream. You'll have the exact same stream facilities available to you there from a Spring Core container handle. Now, in the stuff that we've just been looking at, we saw the injection point perspective, right? The container has managed instances and you interact with it in retrieving those instances. Just to complete the impression here, you can, of course, also programmatically register beans with the container. This is already Spring Framework 5.0 level, so out there for 2 years. It has been out there in a slightly more involved form for many years, where you build programmatic bean definition instances and register those instances. In Spring Framework 5, to kind of complement the programmatic interaction with the container when retrieving beans, we also have nice overloads now for registering beans with the container. Say the register bean methods shown here, they basically just take the component class, or they take the component class and a what we call instance supplier. So just foo.class would say like foo class and default rules. The bar.class variant says like, please register a component of type bar, and whenever you need an instance of bar, please call the instance supplier that I'm specifying here. That's literally a Java util function supplier. What we see here is a Lambda expression bound to it. So the life cycle, declaration, proxying, all of these features are still left up to the container. It's literally just a replacement for like the constructor that you usually would call, or of course a replacement for an add-bean method. So in case you are familiar with the Spring configuration class model with add-bean factory methods for the beans that you're building, this is basically a functional equivalent of add-bean methods. And it's semantically very closely aligned. And this can become a little fancier. The example above is simple. The one below is a little fancier, where bar is assumed to have an object provider of foo argument to be passed into the constructor in its Lambda expression there. And there's actually one more line in the example below, the lazy init call. This is another Lambda expression bound to what we call a bean definition customizer. So setting attributes or setting the lazy init flag or the primary flag, all of those things that you would otherwise maybe express through an add primary annotation or an add lazy annotation on an add bean method. You can set the same semantics here by getting access to the underlying bean definition metadata object before it's registered with the container. So this is kind of the other side of the story, registering beans programmatically with the container. This can be mixed and matched. So if you want annotation-based features as well, start with annotation config application context instead of generic application context. You can instruct the container to perform a class path scan and register further beans by convention. You can register configuration classes. For some beans, you can register instance suppliers as shown here for other beans. So this allows for mixing and matching at every level. But in its purest form, you could also build a quite a minimal focused application context for a particular service of yours. And even if you have to register a 10 or 12 or 15 beans, this is still quite nicely fits onto a single page with this programmatic registration model and completely bypasses any form of class path scan, any form, in this particular case with generic application context, even any form of annotation retrieval. We're not going to look for a single annotation anywhere unless you activate the annotation config features. And we're not even going to use reflection, at least in the version below, as long as you pass instance suppliers for everything, for every single bean in, we're always going to dispatch to this instance supplier. Even for in the example below, even for the default constructor of foo, bypassing reflection. Right? The instance supplier call is effectively an invoke dynamic dispatch straight to your Lambda expression. So completely reflection-free if you want it to be. So, not the focus today, but for a quick impression, to at least show a little bit of Kotlin today here, even if it's not the focus of our talks today, this is the equivalent in Kotlin. We ship Kotlin extensions. Generic application context is a good example, but only one of many. For many core Spring API types, we ship Kotlin extensions, where additional overloaded methods are featured when you choose to use Kotlin. So this looks very similar to the example before, but it actually calls slightly different methods. A register bean method with a k class argument and a register bean method with a k function argument, declared in the Kotlin extensions, and allowing for a very natural and idiomatic use of Kotlin, not having to say class.java, not having to repeat yourself for the instance supplier. We make good use of the Kotlin features here. If you closely look at the register bean bar variant, we're not saying bar.class and here's the instance supplier. We are only giving an instance supplier here, only specifying an instance supplier bound to a Kotlin k function. And k functions come with a reflective API at runtime, so we can safely determine the return type. We know it's going to be of type bar. You don't have to tell us. Whereas for a Java 8 Lambda expression, we don't know. We basically, you know that your code is building a bar, but we can't reflectively see this at runtime. We can see it with a Kotlin function. So I'm making some good use of it, and you can twist the use of the Kotlin language with the inline calls and the inline generics here to get a bit more of a DSL-style experience, a little bit along the lines of the Kotlin DSL in the Gradle build tool, if you will. So there's many variants of this, but just to give you a little bit of a Kotlin impression here before we move on. So there's many things we're doing, and quite a bit of stuff happened in 5.1 and 5.2 recently. I don't see the end of this quite yet, so I'm pretty sure that further fine-tuning is going to happen in our next iteration in 5.3 there. But we're already pretty far along that line, and lots of it has happened actually based on feedback that we got and suggestions that we received of what we could do with a couple of overloaded methods, a couple of Kotlin extensions to make the experience just a little more smoother than it was already. Okay, let's move on to the performance topic, and I'll go into this from a very specific set of perspectives to give you an impression of what it means to tune a Spring-based application, not only from the application level, but also from the framework implementation level. This is, of course, a totally non-trivial exercise, and it has many different kind of effects coming together here. It's not there's no single root of performance degradations usually. So let's start with a somewhat obvious one. If you want the Spring application context to perform a class path scan for you, at runtime, at startup time. This is going to be somewhat costly. We need to go into the file system or into the jars. We need to kind of navigate through the directory structure. We need to introspect the class files and find matching instances according to the stereotype. This doesn't come for free. It may be slow. If your file system, if it's a local file system, no JVM security manager, it might be very fast, but depending on where you deploy, it might also show as a kind of significant effect on startup. There's two recommendations here. One of them, a very general one, we allow for specifying base packages to search from. By all means, narrow those base packages as far as you can. Don't send us through the entire class path. Send us through a subset of your class path by specifying a base package, like com.mycompany.myapp, right? Only packages from that root and below, sub-packages thereof, is then what we're going to search, nothing else. That can significantly cut the time. If that is not sufficient, if that is either not possible or not sufficient, there's another solution in the Spring Framework 5 generation and redone in 5.1 in a slightly different arrangement. There's a build time annotation processor that you can apply. If you're basically saying my class path is complete at compilation time, at build time, then this annotation processor linked into your, as a build step into your build setup, would produce a meta-inf spring.components file where it goes through the class path at build time, finding the matching component instances and enumerating their fully qualified class names in this Spring Components file. When at runtime then, the Spring application starts up, we're going to find those Spring.components files, and we're going to assume that for every jar that this file is in, that it's actually a complete a representation of the matching classes within that jar. So we're not going to even try to search the class path. We're going to use the result as listed in this particular file. This is something to be done consistently, though, otherwise you might be up for a surprise of what's being found and what's not being found. So I strongly recommend applying, if you're applying the indexer, applying to all your application jars. Implicitly, without any further setup, the components can instructions within the application are going to pick it up. So that is one optimization you can take, a common one. There's another, maybe less obvious one. It's mostly about CPU cycles here, not about file system I/O. Annotation processing can be costly, and it's partly because of, partly due to design decisions in the JDK where the way that annotations are represented at runtime is just quite inefficient. They are all dynamic proxies, they are built on demand. Retrieval and inspection of annotations goes through these dynamic proxy invocations. An annotation may look like a simple thing with a couple of attribute methods, but it's actually somewhat involved in what happens in order to retrieve it and in order to invoke it. In an annotation-based application in Spring, with a lot of use of annotations and meta-annotations possibly, right? Building your own annotations where some Spring annotations are declared on your own annotation types. In Spring, we allow you to compose your own annotations. All of this comes with quite a bit of retrieval effort. It turns out that there's quite a few things we can do to optimize the performance overhead of this. Keep in mind, this is only active if you want it to. So if I've been showing a generic application context example, none of this overhead appears there because we're not even going to look for annotations. Only if you activate annotation config through the choice of annotation config application context or through an annotation config configuration element within that context definition, then and only then we're going into the annotation retrieval phase. In 5.2, we re-implemented basically everything. The entire annotation retrieval algorithms have been revisited now and have a new surface called the Merged Annotations API, specifically tuned for annotations according to the Spring annotation-based model. So it's very capable of efficiently introspecting composed annotations in particular. The existing hooks that we had, the existing methods in annotation utils and annotated element utils, all delegate to the merged annotations API, and some of our Spring facilities have been refactored to use it directly now. The overall result is, some more sophisticated interaction for third-party extensions, but for applications, there's a lot of implicit performance benefit. A Spring Framework 5.2 boot to the 2-based application is going to bootstrap much more quickly, significantly more quickly, if it's making heavy use of annotations, than the equivalent application on 5.1. There's a few side effects here that we are still working on. We'd like to enable integration with other forms of annotation registries, other forms of annotation sources, basically, like a generated Gendex index. This is still work in progress. We have yet to find an arrangement where we really, where we feel like recommending it, right? The overhead usually is acceptable in most scenarios. Moving it to build time and creating a build time index that we then read and use at runtime is a solution we've been trying several times, but at this point the performance difference is just not significant enough. The most significant use case might be that other frameworks in your stack are using such an index already and you want Spring to participate in such an index. Like Hibernate being set up with a Gendex index, you might want Spring to participate in it, and that's something we're still exploring, which might materialize in the 5.3 timeframe. It's a positive side effect of the refactoring that we have here. The merged annotations API is a single target for all our annotation retrieval efforts now, so there's also a single point of integration with potential index arrangements or other forms of predefined annotation metadata. So also a bit of an ongoing topic still in that sense. Now, I've been mentioning implicit benefits, right? There's basically just by upgrading to Spring Framework 5.2 or the recently released Boot 2.2, you would already get a significant benefit in startup performance in particular. Annotation processing is mostly a startup time effort that we go through. It won't make much difference beyond startup. Same for class path scanning. Both of those only really affect startup performance. So it's for applications where you find that your startup time is going out of bounds, where you're trying to optimize for startup time. Both of them are sort of implicit. Spring Context Indexer or the annotation retrieval improvements, they all apply to just an application unchanged, just add the indexer, just move them to Spring Framework 5.2 and you'll get performance benefits out of this. Unfortunately, there are limits to how far we can take these implicit benefits. For some performance improvements, we need your cooperation. We basically need you to reconsider some of the programming model elements that you're using in your code. The most extreme variant is programmatically registering all your beans. This is by far the most efficient variant of setting up a Spring application context if you care about CPU cycles spent on startup. In the purely programmatic phase, the register bean stuff we've seen before, there would literally be no component scanning, no reflection, no annotation retrieval if you don't need it, if you don't want it to be there. But that's a very extreme kind of perspective. We realize that most applications prefer to work with the annotation-based model, the larger they get in particular. Now, in the annotation-based model, there's a few new twists as well that we have. A new one in 5.2 is that for configuration classes, you may choose to opt out of the CGlib subclass generation for configuration classes. There's a specific feature in configuration classes where one of your add-bean methods might want to call another add-bean method in the same class or in another configuration class, and you want us to intercept that call. So that when you delegate from one add-bean method to another, it's not a straight method dispatch, but rather an indirection through the container, where the container is going to return the managed instance in the current scope for that bean that you're calling. So the call that you're performing is sort of an indication to retrieve a certain bean from the container. You might not actually use this. Many configuration classes don't use these cross-adbean method calls. They just have independent adbean methods that don't call each other, or that only accept other beans through arguments or through dependency injection, not through adbean calls. If that is the case, you may opt out of this proxying of bean methods through a new flag on the configuration annotation type, proxy bean methods false. We don't expect application classes to do this all the time, although you may, if you know that your configuration classes can benefit from this. It's something we have in particular been applying to Spring Boot auto configuration. So in Spring Boot 2.2, quite a few of Spring Boot's own configuration classes in its auto configuration model declared this flag now in order to skip this interception feature, which means we don't have to create a subclass that overrides those methods and intercepts those calls. Class definitions at runtime can also be costly, and we're trying to cut it down if necessary, if possible. And another variant of this also shows up for AOP proxies. Generally speaking, interface-based proxies are faster to set up on startup than zglib proxies. In both cases, we have to define classes at runtime, but the Java-lang reflect proxy feature in the JDK is faster than the zglib enhancer. So if you care about startup performance or to some degree interaction performance, interface-based proxies may be your mode of operation. And even in recent Spring Boot versions, you may choose to, for this particular purpose, to switch the proxies from their now default target class model. You may switch them back to interfaces through the Spring AOP proxy default proxy mode proxy target class false flag in Spring Boot, right? At the core framework level, interface-based proxies actually remain a kind of default feature anyway. We see this as opting into target class proxies when you choose to use zglib. There's other implications here. If you'd like to design an application that doesn't do any runtime class definitions, you might not want to use zglib proxies at all. We'll speak about Graal in a moment, where interface-based proxies are supported out of the box, but zglib isn't. Before we get there, a quick note. There's many things you can tune at Spring Framework level. Keep in mind that, of course, in any kind of larger setup, in any kind of complete application, or particularly Spring Boot setup, it's not just Spring Framework facilities that are involved here. Bootstrapping Hibernate is very expensive in its own right, or can be at least. I would highly recommend to check out the latest improvements that they've been doing in Hibernate. Hibernate 5.4.5 and higher come with significant performance improvements and tuning options for a faster bootstrapping of Hibernate. We have a couple of interesting features at Spring Boot level as well, where Spring Boot configures the core container facilities to bootstrap the persistence provider, like the Hibernate Session Factory, in parallel to the rest of the application. So if you have that CPU power available on startup, it might make sense to spin this off into separate threads. But tuning Hibernate itself is an important part of this game. And another common suspect is Jackson. By all means, try to be on the latest Jackson releases, not only for some fixes to potential vulnerabilities there, but also for efficiency improvements. Unfortunately, there's only so far you can go with parsing JSON all over the place. But Jackson itself, as a side note here, Jackson itself comes with alternative data formats where the primary benefit is they are more efficient to parse at runtime. So if you can switch to an alternative format for service-to-service interaction, you might want to go with like Smile or Seaboard instead of standard JSON, just for the runtime efficiency of it all. Now, before we move on to a little bit of reactive discussion at the very end, two forward-looking notes. A huge topic for us is GraalVM in general. We're very much looking at the performance topic, not only from our framework perspective, but from the perspective of the entire stack. So tuning a regular hotspot JVM, of course, on the one hand, or using alternative JVM implementations for certain performance characteristics that are important to you, right? This is something that we provide guidance on at this point primarily. You may choose to use OpenJ9, IBM's OpenJ9 as an alternative to Hotspot for certain scenarios. It's not only about startup time, it's also a lot about memory consumption and efficient garbage collection. There's quite a range of options we have out there in the meantime, all around OpenJDK mostly. But then there's also GraalVM as a specifically interesting piece of technology coming out of Oracle Labs specifically. We have been considering Graal compatibility concerns last year already, so some of it is in 5.1. The GraalVM is actually two things, so can't go into too much detail at this point here, but GraalVM basically is a replacement for the JIT, for the just-in-time compiler in Hotspot, where the good old C1, C2 arrangement is replaced with a more modern implementation in the form of Graal's JIT. But for our purposes here, we're really looking at the ahead of time, the AOT features in Graal. It's also called the native image model. The Graal sub-project is called SubstrateVM, where a Java-based application, a Spring-based application, can be turned into a native image with a quite different mode of execution at runtime. A native image is essentially the outcome of a build time task that it can actually run for several minutes. It's quite costly, but that produces a very much tailored executable. That's not really your regular JVM. It contains all the class definitions. It contains all the information needed to run this Java-based application, but in a quite different mode of operation. There's no hotspot. There's no hotspot optimizations, but at the same time, it starts up almost immediately. So there's very immediate startup and very reduced memory consumption. So if you care about startup time, or if you care about minimal memory consumption of your process, then native images are certainly a tool with a lot of potential here. Unfortunately, this also means a lot of constraints. No runtime class definitions. Reflection is supported, but only if the native image tool has been provided with the corresponding class information. So we basically need to configure the native image tool to generate reflective information for all the types that you intend to use reflection on at runtime. In a Spring-based application, that would typically be your annotation-based components that are going to be reflectively called. So just by configuring Graal accordingly, or by applying a corresponding Graal feature implementation that does this automatically, you get closer to a kind of out-of-the-box experience trying to make a Spring application work on Graal. There's a wiki page listed down here where we summarize the current state of the art for Graal native support with a Spring-based application. We have prototypes of our own. We have quite a bit of R&D on our own invested in this already towards more of a first-class experience that we intend to deliver in the Spring Framework 5.3 timeframe. This would still be a lot of guidance. There are still a lot of constraints that you need to keep in mind to adhere to, but we're trying to take all the pain away the pain of manual configuration. So I expect that there would be an out-of-the-box feature implementation for the native image tool, a Spring feature that can be plugged into the Graal native image tool that uses Spring conventions to identify the reflection metadata that is needed in the native image. Many other little fine-tunings have been sneaked into Spring Framework 5.1 and 5.2 already, where we're trying to avoid internal issues where we run into Graal barriers. So we're not using unnecessary reflection anywhere consistently now. If parameter name discovery doesn't work, we simply skip it. This has all been sneaked in order to adapt to Graal conventions and to Graal constraints and limitations automatically. So lots of potential here if you care about performance tuning for startup and if you care about the memory consumption profile of your deployment unit. And the other one that I'd like to quickly name drop is Project Loon. one of the most interesting initiatives in OpenJDK itself, maybe next to Project Valhalla and its value types that are now named inline types. It's another story, but for our purposes here, Project Loom, with its use of fibers, which have just been actually renamed to sort of lightweight threads. So the official name is going to be lightweight threads. They're not going to be called fibers at the API level. This is essentially a rethinking of Java threading, where within the JVM, a very lightweight representation of an execution thread and the state attached to it can replace a classic operating system bound thread, allowing for a different category of scalability with traditional threading setup, with traditional thread pools. That instead of like 150, 200, a couple of hundred threads, you might be able to set them up with literally thousands of threads that can be very efficiently managed and that don't consume all that much memory because they're managed within the JVM in a very efficient fashion and don't occupy operating system resources beyond this. This has a lot of potential to bring some new life back into traditional interaction architectures, like Spring MVC on the servlet stack, using JPA, Hibernate, right? JDBC maybe. For those kinds of architectures, in order to make them scale without many changes at all, or without any changes at all to the application, the fiber model, like Project Loom, lightweight threads, are probably the #1 candidate to look forward to for basically scalability benefits and memory consumption benefits that are going to be almost transparent. For many purposes, they're going to be a transparent benefit just by upgrading to an OpenJDK version that has the lightweight thread model built in and configuring the thread mode, the execution mode for threads accordingly. An existing Spring-based application, Spring MVC-based application might immediately benefit from it without any further changes. All right, so much on a forward-looking note. We don't know when Loom is coming. But this is quite connected to our reactive efforts, since another way, of course, the other way, to address scalability concerns is reactive programming. And from our perspective, both are an important part of the toolbox, right? So there's going to be, in all likelihood, some new, fresh life back into Spring MVC, back into traditional interaction models with blocking semantics, but a different degree of scalability that we get through Loom. Or you choose to go into reactive programming, where you build reactive pipelines that can be efficiently dispatched to from an event loop, where the individual steps taken within that pipeline don't actually block at all. They interact with non-blocking data store APIs, and they integrate with a non-blocking web architecture. That, of course, is the other way of addressing scalability, but it's not just that. It's just a different way. It's also a different way of expressing yourself. It's a different way of coding, a more functional style of coding, more collection stream aligned way of coding. So we have had reactive Spring this morning, of course, so I'm not going to rehash the basics here, but let me point out just a few things that might not be all that obvious. For a start, reactive endpoint models, as we see them here for web architectures, are not exclusive to the Webflux stack. There's a constraint, of course. If you're building a Spring Webflux application with an event loop architecture underneath the covers, maybe based on Netty, you have to design all your web endpoints with the reactive programming model. However, this very same endpoint design, like request mapping methods that return a reactive type like mono or flux, a reactor mono or a reactor flux, the same arrangement, the same programming model element works on Spring MVC as well. So what happens if you take a controller with endpoints such as these here and you deploy them to Spring MVC on a dispatcher servlet, on a servlet container, like standard servlet container? What happens? Well, we are trying to do the best we can with the signatures that you're giving to us. We understand that those are reactive return values. We switch the servlet request, the servlet container, into async request processing. We use servlet async streams to adapt the reactive streams publisher that you're giving to us to the servlet async stream model. And there's even a little bit of back pressure with servlet stream availability indications in order to make your endpoint work in a non-blocking way. This actually works quite well. It's not as efficient and as pure as an event loop-based architecture on Webflux, but it is a very reasonable way of integrating some reactive programming elements into a Spring MVC architecture for certain endpoints, maybe just for server-sent events or just for other long-running kinds of endpoints. There's the reactive transaction support that we've been showing also this morning. That has also been a piece in the puzzle here. Like previously, we had at transactional declarative transaction support for like regular, basically data store interaction methods, where we would intercept the call to the method, bind the transaction to the thread, call the method, and then return and do a commit or rollback. Does that make any sense with a method that builds a reactive pipeline that doesn't actually do data store operations? It rather builds a pipeline for data store operations? It doesn't really, right? So in Spring Framework 5.2, we have another mode of transaction execution, reactive transactions, backed by a reactive transaction manager. If you apply declarative transactions to a signature that builds a reactive pipeline, we are going to decorate the reactive pipeline. We're not doing thread-bound transactions. We are building a transaction context, adding it to the reactor context, applying a transactional operator on top of the pipeline that you built, so that the data store operations within that pipeline can participate in the transactional resources, getting them out of the transaction context. This is a reactor feature, so we're closely integrating with Project Reactor's context facility here. This is in particularly useful with reactive transaction manager implementations where the drivers have transaction features. The reactive drivers have transaction features built in. At the moment, this is true for MongoDB, for Neo4j, and for R2DBC, for our kind of JDBC on reactive sort of effort. R2DBC, of course, providing access to all the R2DBC drivers, to the Postgres one, to the other efforts there towards MS SQL Server. There's even a plan to build an OJDBC 20 based version of R2DBC for the Oracle database. So this implicitly gives access to quite a lot of relational databases in the meantime through R2DBC integration. The setup is as unified as possible. So it's at-enabled transaction management. It's the same setup rules as with regular transactions. The only real difference in setup being you need to declare a reactive transaction manager implementation that our transaction interceptor can pick up and apply to your reactive pipelines. So it's very much driven by the availability of reactive transaction implementations in your target data store. So it only really works with R2DBC, MongoDB, and Neo4j at this point. Another major storyline that we've been showing this morning in particular, but let me rehash it quickly here, is the RSocket integration. Actually, more generally speaking, our reactive messaging endpoint model. This is instead of web request mappings, we're doing message mappings where your endpoint methods accept an incoming payload, message payload, and they can return a reply to that payload where a reply is being sent back on the same channel. In the reactive programming model, this can come in many ways. There may be a pre-parse payload that you accept. There may be an incoming reactive streams publisher that delivers the payloads as they come in. In particular, you may choose to return a reactive streams publisher, like a mono Flux here, where you're basically saying, okay, for this incoming kind of message, I have a whole sequence, a long-running sequence of messages that I'm sending back. And I'm expressing this through a reactive pipeline that I'm returning from this message mapping methods. So programming model-wise, this is very close to our established web endpoint model, to the web controllers and request mapping variants that we have there, just using the message mapping model. It's also very similar to the way we handle other messaging protocols, like Stomp on WebSockets is very similar to the arrangement here. Now, almost last year, but not least, the application event facility, like event listeners, callbacks from the application context for events that have been published and are being propagated to corresponding listeners. You may also use some reactive programming now for event listener implementations, where if an event comes in, you're building a reactive pipeline, you're returning it, and our event multicaster knows, okay, this is a reactive type, I'm going to subscribe to it, I'm going to integrate it into my multicasting efforts. This is in particular designed to be a nice complement in a purely reactive architecture. If you're building a Webflux application where everything, the web endpoints, the messaging endpoints, the service declarations, the repository declarations, they all use reactive pipelines. Now you're also able to express event listener semantics through a reactive pipeline and to get some individual asynchronous execution for each such listener through that return type declaration. And it works for regular reactor like mono implementations. It also works for a completable future, kind of as a side effect. And that's quite useful for event processing in particular, where it's often just a simple async execution with not much back pressure involved. The one note, quickly mentioning it here, is that whenever we say reactive API types, and you might have heard us say this a few times, we primarily mean Reactor Mono and Flux, reactive streams publisher implementations that come with Project Reactor. Wherever we support those, reflectively in particular, we also support the RX Java equivalents, like Flowable, Single, and so forth. You could even choose to use RX Java 1 still. You could use Java Util Concurrent Flow publisher implementations. This is the reactive streams repackaging in JDK 9 and higher. If you can find any implementations thereof, all the ones that I'm aware of actually implement the canonical org reactive streams publisher. And in most places where we support reactive types, we also support completable future as a kind of slightly simpler, single element based, non-back pressure driven variant. It's not really a full reactive type, but it's often a nice way of coding a simple asynchronous task. And conceptually speaking, where we support reactive return types, we also support completable future. A little twist towards Kotlin at this very end here. You might have noticed there were some blog posts around it and some recent presentations dedicated to it. We support Kotlin coroutines now as a brand new feature, a Kotlin language innovation that we adapt to our reactive stream stack underneath the covers. So it's Kotlin coroutines on Webflux primarily that we support right now. We're going to extend its reach a bit in 5.3 towards reactive transactions, towards reactive endpoints in Spring MVC. And the way we implement this is that the Kotlin compiler provides basically compilation down to a reactive pipeline. It takes a Kotlin suspending function, compiles it to a Kotlin flow implementation that we adapt to our reactive streams infrastructure underneath the covers. A very immediate, very direct translation of Kotlin coroutine semantics onto our reactive streams architecture underneath the covers. Just like if you chose to use RX Java. That same sort of adaptation happens underneath the covers here. All right, that's what I'm going to leave you with. All of the stuff that we've been talking about without a forward-looking note is available in Spring Framework 5.2 already, GA for a couple of weeks. There's Spring Boot 2.2, which just is a couple of days old at this point. Also GA already. It brings in Spring Framework 5.2, it brings in Spring Data more, and it also allows you to consume Spring Data R2DBC and the reactive transaction implementations in Spring Data along that line. It also comes with out-of-the-box RSocket support for the first time in Spring Boot land. So it's an entry point, a convenient entry point to many of the things that we've been talking about both this morning and this afternoon. So thanks for your attention. I'll be up there in the discussion zone in just a moment for any questions you may have. Thanks.
Yes, thank you, Juergen.